Let's do a quick review of the last lecture where we spoke about the applications of Bayes' theorem, and then we started talking about Bayesian networks. All right, Bayesian networks being an extension of Bayes' theorem to slightly more complex situations. And we'll continue to speak about Bayesian networks most of today. And if time permitting, we will then start the next major section of this course, which is probabilistic reasoning over time. All right, so now time will be involved, and we will start looking at things like Markov processes, Markov chains, and basically the idea is to be able to look at Markov decision processes. Okay, so this is what we spoke about last time. This was an example of the Bayes theorem that we talked about. Students at IBA, we looked at the tree representation. Just want to talk a little bit about this particular tree, and this will come up again. So over here, when we spoke about probability of B, we said that probability of B is the sum over A and C, okay? And this is something that will come up again. This is also referred to as marginalization or marginal probabilities. All right, this is what we already spoke about this. And A, of course, is the product of probability of A and the conditional probability. There was some confusion about this last time. So we'll talk about this a little bit more today. And then we talked about prior and posterior probabilities, cause and effect, and looked at examples from legal cases as well. And then we went on to talk about probabilistic reasoning. And we did a little bit of a review about random variables. And this was a table that we talked about in terms of marginal probabilities. If you remember, we said that if you just sum these up, then the probability of T is simply the probability of T with CS and non-CS, okay? Similarly, you can see that the probability of CS is simply the sum over the other variable, which is techie or non-techie, all right? So this is how we calculate marginal probabilities using joint probabilities, right? So these are the joint probabilities, okay? And these are the marginal probabilities, and they all sum up to 1. We started talking about Bayesian networks, and we said that it was a directed acyclic graph. And we looked at the earthquake example. This is often also called a burglary example or an alarm example. You can use your favorite nomenclature for this. But here, the example was that you had independent probabilities, so independent events being burglary and earthquake. And then, and there's certain probability of this happening. I've made slight changes over here to be consistent with the book so that you can check your answers. And then we have conditional probabilities, the probability of an alarm given that a burglary happens, or the probability of an alarm given that an earthquake happens. But here it's given as a joint probability. In other words, you don't really know what's the probability of an alarm only given burglary. You're given what is the probability when both of these happen. And there are 4 combinations of these, right? So you could have both alarm, both burglary and earthquake happening, and none of them happening, and the other 2 combinations. So the joint probabilities are only given, the joint conditional probabilities are only given. Today we'll talk about how do we actually get the probability of A only, or probability of A given B, okay? And that will use marginalization, the concept of marginalization or marginal probabilities, okay? Then we'll go on to talk about what how joint probabilities can be determined over here, all right, and so on. So this particular example embodies a lot of concepts. So please do pay attention so that you don't get confused and lost, okay? We'll try to go over each one of those concepts one by one and make sure that you grasp each one of them before we go to the next. So, and we'll try to keep it simple. In other words, we could initially just look at the top half, all right? And then later on, we can start going towards the bottom half as well. Okay, but I'm just using one example so that all the concepts are made clear in one example. Okay. The other thing that we talked about is conditional independence, and this refers to something that that we started talking about last time, and we said that can you think of real life examples where you have conditional independence? In other words, let's say there are three events, A, B, and C, and C only depends on B. B in turn depends on A, but conditional independence means that given B, C is independent of A. Okay, I'll repeat that. Given B, then C becomes independent of A. Okay, and now I want you to think of some real life examples, and we sort of, towards the end, we talked about an example of this lecture, for example, that let's say A is the probability that, time goes up, right? So it's quarter to 4 and you're supposed to disperse. And let's say B is the event that I actually let you go, okay? And C is the event that you guys actually leave. They're all, you can see they're all linked, right? But for most of you, unless I actually let you go, regardless of the time, perhaps you will listen to me and you will not leave the auditorium, okay? So I can say for all of those people who are obeying this particular process, C is independent of A given B. As long as I'm asking you to stay here, you don't care what time it is, all right? You have to stay here. Maybe there's a quiz or final exam or something. I'm forcing you guys to stay here. But some of you may actually leave. So those are people who are actually independent of B. But let's say so I hope you understand this example that given B, C is independent of A. Individually, B is dependent on A. So I hopefully am going to, terminate the class when. So A is time goes up, goes up, all right, for the class. B is that I let you go, okay? I terminate the class, and C is where you guys actually leave. So this is a chain in which C, I'm claiming, can be independent of A given B. But let's think of other examples. So think of your examples. This may not, the example that I gave you of this may or may not make sense, but think of other examples in your lives where you have three events, where the third event is given the middle event, the third event is independent of the first event. Ji. Yeah. Okay. So the exam, let's say it's an A-levels exam, and so the person in the middle is who? Okay. Right. So in a sense, what you're saying is that if you have an exam preparation, then C is going to independently grade you guys, irrespective of how well or worse your instructor actually prepared you, right? So if you're in school and your school is actually preparing you for an A-levels exam, now these guys don't really care how well you prepared. They're going to look at your results in the actual exam, okay? So that's a very good example. Think of any other example, or is that sufficient? I think the point is driven. Let's just think of courses. So let's say that if you have course prerequisites, can you think of is there some conditional independence? Let's say these are courses A, B, C, D, E. Let's say intro to AI is over here, and this is data structures. And let's say this is introduction to programming and introduction to computing, all right? So data structures may require that you pass IP and IC, okay? You can't take data structures unless you actually pass A and B, okay? But intro to AI only has data structures as its prerequisites. Let's assume that, okay? Now, given that you've passed data structures course, what I'm claiming is that this prerequisite is sufficient. of the earlier prerequisites, because the only prerequisite for AI is data structures. So given that you've passed data structures, the previous, whether you've passed them or not, hopefully you've passed them. That's why you were able to go to C. C depends on A and B, but E only depends on C. Okay? So it's a conditional independence, and you'll come across this in the whole of today's lecture again and again. Similarly, D is only dependent on C. If C is true or false, it doesn't really care about the earlier values. Okay, so this was just this example. Okay, next concept, and these concepts will build up your understanding of Bayesian networks. Okay, so it's important to be able to understand these. So next, again, the concept is that of marginalization. So we've already seen that example in the computer science students, and we said that the probability that you are, let's say, a techie is simply the probability that you are a T as well as CS and non-CS. So given the joint probability A and B, how would you calculate probability of A, given that you have A and B, right? So you've got the joint probability distribution, okay? A naught, B naught, and these are the combinations A bar B, A B bar, and A bar B bar. Now, how would you calculate the probability of A? So no, you don't know the individual probability of B yet. All you know is the conditional probabilities. You're only given these joint probabilities, not conditional. These joint probabilities are only given to you. You know this, you know this, you know this, and you know this. So now you want to find out the probability of A, D. Just add the columns, right? It's very simple. That's called seems like a complex concept, marginalization, but all it says is that you take the sum. So probability of A is simply the sum over all possible B values of the joint probabilities. Okay, so that should be clear now. And similarly, if I say that what is the probability of B, probability of B, it would be what? So you would do a summation horizontally over here for all possible values of A. If I said what is the probability of B bar, what would you do then? You would simply sum over with B bar given, you would sum over the other values of A. Okay. So this is how you do it. Probability of A would be probability of A multiplied by probability of B plus the probability of A multiplied by the probability of B bar, assuming that B and B bar are the only two possible values. But if there are more values of B, you'd sum over all the possible values of the other variable to be able to get the marginal probability of the first variable. Okay, so hopefully that's clear. We're going to take these probabilities and we're going to sum over the possible probabilities of E. Okay, so what are the two conditions? We need to sum over probability of A given B comma E, and this is 0.95 over here. Okay, multiplied by the probability of E, which is 0.002, and then we multiplied by the probability 0.94 over here. Okay, and the other value of E, not E. So we multiply that with probability of E bar, and that becomes 1 minus 0.002. Okay. So let's see if we can do this one now. Let's take another example. Probability of A given B bar. Okay, so this was probability of A given B, and we summed over these two cases. If you're looking at probability of A given B bar, we should be able to sum over these two cases. Okay, so we're going to do 0.29 multiplied by the probability of E here, which is 0.002, multiplied by this particular value, 0.001, multiplied by probability of E bar. Yeah, there's a mistake over here, so this should be 1 minus 0.002. Okay, good. People are awake. So far so good. Hope that I didn't lose too many people, but let's go forward. So now a bigger question is, how do we calculate just the probability of A? Okay. So far we've done probability of A given B, all right? And we looked at these two cases. So probability of A given B was summed up over these two cases. If you want to do simply the probability of A, how would you do that now? So now we should be able to sum over all four cases, right? So we would say it's the probability of 0.95 multiplied by probability. So let's just go to the solution. So what we'll do is we'll multiply 0.95 over here with the probability that both B and E are true. So now we're trying to get rid of both B and E. Okay. So now we're going to sum over all the possible combinations of B and E. So now there are going to be four possibilities. Okay. So we're going to take 0.95 multiplied by the probability of both being true, which is 0.001, 0.002. Why? Because this is the case where both of them are true. Okay. Then we're going to take the case where 0.94, where this is true. Okay. And the probability of that being of burglary being true is 0.001 multiplied by the probability of E or earthquake not being true, right? So that's going to be 1 minus 0.002. Okay, so far so good. Next, we're going to take this probability, 0.29, and we're going to multiply it by 1 minus 0.001. Okay, and we're going to, this is true over here, so we're going to simply multiply it by the probability that E is true. Okay, so we got this right. And then finally, we're going to take this and we're going to say probability of both of them being false, which is 0.001 multiplied by 1 minus this, multiplied by 1 minus probability of E. Okay, so this is how you'd sort of marginalize certain values out. Okay, you'd simply sum over all those values of the variable that you're trying to get rid of. Okay. Right, so that was a little bit about marginalization. Now, the next concept is a causal relationship. Now, remember, where did we come up with causal relationship earlier? When we were talking about the Bayes theorem, right? Where we're simply saying that given a particular symptom, what's the probability that a certain disease happened, okay? So now what we're saying is that given that an alarm has happened, so this is sort of like the symptom, okay? What is the probability that this was the disease, all right? Or this was the cause? So what's the probability that either the burglary was a cause or the earthquake was a cause given a certain symptom or an alarm, okay? Given the effect, what is a cause? So for over here, then we can simply apply Bayes theorem, right? Because this is a causal relationship. And we already know how to solve causal relationships. So how would we solve this? You know Bayes theorem fairly well. So how would we do it? Probability of A given B multiplied by probability of B divided by the probability of, okay. So that's your standard Bayes theorem. So probability of A given B, okay, multiplied by the probability of B divided by the probability of A. That's your standard Bayes theorem. Okay. Now the question is, do we know these parts, right? Do we know probability of A given B? Do we know what probability of B is? And do we know what probability of A is so far? How do we know that? We just did that, right? We did using marginalization. So we said earlier that probability of A can be calculated. Similarly, we can calculate the probability of B using marginalization, okay? And we said that probability of A given B can also be calculated using marginalization, where we simply we sum over all possible values of B, okay? So you simply using the concept of marginalization, we can now solve the causal relationship of B, what is the probability of burglary given that an alarm has taken place? Okay, so we've combined a few concepts so far. We've combined the concept of marginalization and Bayes' theorem to be able to solve a causal relationship. Okay, and so far we've gotten till the top part. Okay, we haven't looked at something further down. Now, so this is done. We can actually solve a fair amount of the basic query. So if you have something like this, a complex problem like this, what are the kind of questions that you would want to answer? Okay, are these the kind of is this the only question that you'd want to solve? That given that an alarm has happened, what's the probability that burglary happened? What other questions would you want to solve? G. So why is it that Mary or John is calling? That's what you're saying. So let's say that, or in other words, what you're saying is that if you get a call from, let's say, John, then what's the probability of, so what is the probability that he's calling because of an earthquake or because a burglary actually happened? So you're trying to determine the cause of the call. So you maybe got a missed call from John, right? But now you're a little concerned. Was there a burglary in my house, or was it just you're in Stanford, so the probability of earthquake is very high, burglary is low? This is different from the earlier example, which was Karachi, but here this is like something in the US. Okay, in Pakistan this would definitely be much higher. But you're basically trying to solve. You're trying to figure out what is the probability of a certain cause. Okay, but here the problem that you just pointed out, that John is calling, given, and now you're trying to figure out not just the probability of an alarm, but you're going 2 steps behind, right? So now, is that an easy problem or a difficult problem? So far, we figured out the probability of an alarm, right? Or probability of B given A. So earlier we did probability of, we just did probability of B given A over here. But now what you're suggesting is, what is the probability of B given, not A over here, but we're going even 1 step further down. Okay, we're saying what's the probability that given J, what's the probability of a burglary? Okay, so we're trying to actually go 2 steps deep. And if you can imagine that this is even more complex, then you could have something way down at the bottom at the leaf, and you're trying to find out what is the probability that the cause was one of the things right at the top. Okay, so this is by no means an easy answer. Okay, as it is, it's becoming complex. But what we'll see is that if you understand the basic concepts, then there are tools. Fortunately, all right, we're software developers, so software developers naturally have a tool for this, and there are software tools which will, if you can frame the problem correctly, then you don't have to go through all the mathematics. Okay, you can just use certain tools. For example, there's Genie and others which will solve the problem, but you just have to frame it right, and then the solutions will start popping out. But of course, you have to know how the concepts are working. Okay. And if there's a mistake and if you have to actually develop those tools, you should be able to know how to develop those tools as well. Okay, and to be able to figure out whether the tool is actually doing it right or not. So, so that was one of the things that you might want to figure out, but that's a little further down, and we're actually not going to solve this problem. Okay, we're not going to try to solve what's the probability of burglary given J. Okay, that's a little complex, but we'll try to get somewhere close to it. Okay, and we'll leave that to a software tool. So now the next thing that you will need to know as you go forward is the joint probabilities. Okay, in this kind of a Bayesian networks. So the joint probability is the question that, let's say you had all of these. What's the probability that John calls, okay, and Mary calls, and there's an alarm, and there's a burglary, and there's an earthquake? Okay, what's the probability of all of them happening? Is it 1? Somebody's saying that it's a 1. Okay. So in other words, what you're saying is that there's only a 1/10 probability of a burglary happening. There's only a 0.2% probability, 2 in 1,000 chance that an earthquake will happen. And it's only because when those two happen that you get an alarm, and it's only when an alarm happens that you likely have John or Mary calling. Now you're saying that the joint probability that all of those things will happen is 1. Not making sense, right? The joint probability is probably going to be fairly low. The probability that an earthquake also happens and a burglary happens, I mean, hopefully, even if you're living in San Francisco where earthquakes are very frequent and there's some burglaries happening, even there, hopefully in your lifetime, that doesn't happen, right? So it's not, hopefully it's not going to be 1, right? It's going to be much, much smaller than 1. It's probably, if you just have to take a wild guess, what would you say is the probability of all of that happening? Just a very intuitive guess, okay? Given that burglary is 0.001, we've already found out what's the joint probability of just these two happening, right? So what is the joint probability of both B and E happening? It's going to be remember they're independent events. So it's going to be the product of those two. So just these two happening, the probability is already gone down to 0.002, which is like 2 times 10 to the power minus 6 or something, if I'm not mistaken, right? So it's something extremely already very small, the probability of both an earthquake happening at the same time as a burglary, right? So we're living in a safe world, all right? Good to know. And now what we're saying is we're simply adding on some probabilities. We're saying that, well, let's say the remote chance that both of these events happen, okay? We want to make sure that the alarm also takes place and those two guys that you had, maybe you're paying them something, that you're not just good neighbors, you're paying them something and you're expecting that they will actually be responsible, that they also call you. So it's going to be, you think it's going to be lower than this, or it's going to be slightly higher than this? It's going to be what? It's going to be higher. Does the alarm always ring? So already the alarm, there's a probability that the alarm will not ring, right? So it's already going to be lower. And then there's a probability that John will also not be, he's also not very good. There's only 90% chance that he actually calls you. So now it's going to be even lower, right? And then Mary, of course, listens to our music, so that's even lower. So the joint probability is going to be, is it going to be lower than this or higher? It's going to be lower, right? And how much lower is it going to be? It's not going to be 0. It's all, well, this is approximately 0 as well. But when you get into small numbers, you have to be more accurate. You can't just say that this is approximately 0, right? That's not good enough. If you want to make a first order approximation, you can say 2 to the power minus 6, or you can say even 1 to the power minus 6. But saying that that's 0 is not going to work out. Okay, that's a 0th order approximation. Yeah. So basically, how would you calculate that? Exactly.
Multiply the probabilities.
So you'd multiply it with each one of these other probabilities. Okay. So basically, what you would do is you would and it's not completely and you've got you sort of in the right direction of the marginal probabilities, but there's a theorem to help you. Okay, this is theorem equation 14.2 in the book. What it basically says is that you take, for each one of these values that you take, you take the conditional probability with only their parents. So this is an important thing. Okay, it's not completely intuitive, but this is an important theorem which says that you must take the individual. It's a product, first of all. Okay, it's a product of what? It's a product of each one of those values. So we're going to multiply it by probability of J, multiplied by probability of M, multiplied by the probability of A, multiplied by the probability of B, and multiplied by the probability of E. Okay, I'm putting in a bit of space over here. Okay, why do you think I'm putting in some space over here? Because it has to be conditioned on what? it's right here. It has to be conditioned on not everything else, but only their parents. Okay. So what would we say? Probability of J given A. So the parent is only A. Okay. Parents, why? Because in some cases you have two parents. But if you only have one parent, you're only going to use that parent. You're going to exclude everybody else. So what's this going to be? Probability of M given A. Probability of A given B comma E, right? Why? Because now there are two parents and this is a plural. So you have to condition it on both the parents happening. Okay. A probability of B given, it's independent. Very good. So finally we get something which is not dependent on anything. So it's simply going to be probability of B. Okay. And what about this? Again, there is no parent, so it's simply going to be probability of E. Okay. So let's take a look at this. Did we do it right? Probability of J given A. Okay. Probability of M given A. Right. Probability of A given BE. All right. Probability of A given BE and probability of B given EE. Sorry, probability of B given. Well, so this is now written as a joint probability. Okay. Why? Because you could simply say that they are the product of the probabilities. You could say that these two are simply the joint probability. Okay. Two different ways of doing it. Ultimately, you actually write it as a product of the individual probabilities. So, so you can see that if you wanted to take another example, that you're simply saying, what's the probability of this happening? All right. So we want to say, what's the probability that there's no burglary, there's no earthquake, but there's an alarm and John calls and Mary calls, right? So what are we going to do again? We're going to take all of those cases again, and instead of using simply B, we're going to use the not B. Okay, so instead of saying A, because now we have to use the parent's probability, so we're going to say A, not B, and not E. Okay, and then we're going to do the multiplication with the not values. Okay, so hopefully do some examples as well so that you actually get into the practice of actually working this out. Okay, so that was another major step of joint probabilities. All right, and by the way, in case somebody was wondering, we're simply writing A comma B as a shorthand of A intersection B, A and B. Okay, that's sort of understood. So let's just do some more examples. Okay, and we're just going to use variable V over here. It could be A, B, and C, but let's just use B. So what would this be? Just using this theorem 14.2. Okay, calling it a theorem, but use that equation. So now you could either go backwards or you could go forwards. Okay. Here, what we've done is we've gone backwards, right? So we went from the tail and we went upwards. But you could have very easily gone forward as well. So let's try to do it in the forward way. Forward is a little bit easier. So what we could do is take the one which has no dependence first. Okay. So it would be probability of A. Then we would do the next one. So what would this be? V given A. Okay. And next would be probability of B given V. Okay. So this is all there is to it. This is the joint probability, but based on the parents. Okay. So what about this case? Let's go forward as well. So probability of V multiplied by A given V multiplied by probability of B given V. Okay. So far so good. What about this particular case? So A and B are now independent. So what would we do? So probability of A comma B, or we could simply write it as probability of A, B, right? Because they're independent, multiplied by of V given A comma B. Very good. So you'd have to use both the parents in this case. Okay. So hopefully we got this right. Okay. Right. So that looks right. I think we've got joint properties figured out. Okay, now the next, again, major step is conditional probabilities. Okay, now this is not the complete conditional probabilities, but this is a slight subset of that conditional probabilities. So what we're going to say is if you say, let's say that we have this particular problem, right? We want to say that what's the probability that, let's say, Mary calls given all of these guys above, okay? Given that J calls, the alarm rings, the burglary happens, and the earthquake happens. So what do you think that should be? So all we want to know is not the complete solution, but we want to put it as a conditional probability. In other words, we're trying to simplify it and get a hint from what we're saying over here at the top. So we're not trying to completely solve this, but we're trying to say, can this be written as a smaller subset? Do we really need to write all of this? Or can some of these be removed? Look at the conditional probability tables, okay? The conditional probability tables are already giving you a hint. So here, what could we actually remove over here? We're saying the probability that Mary calls, we've given all of these other guys, right? But does it really depend directly on all of them? What does it directly depend on? Only on the alarm, right? And we already have the answer that the probability of M given A is already given. Okay, so what does that tell you? Do we really need to have all of these other variables in there? Conditional variables? No, we could simplify it. Okay, we're not saying that we're going to completely have the marginal probability, but we still want to have a conditional probability, but we want to remove unnecessary conditions. Okay, and what we can see is that the alarm is the only one which is really important. We can actually remove these guys. Okay, so we can simplify this and simply say the probability that the Mary calls, given all the others, we can actually remove any one of them. We can simplify this to be only the parents. Okay, if the parents are a subset of the other guys. Okay, so who's the parent over here in this case? Parent is what? A is the parent. Now, is the parent a subset of J, A, B, and E? Yes, clearly, right? Because the parent, is right here. So the parent belongs in that entire set. Okay. So if the parent belongs in that entire set, we can simply remove the other guys and we can only leave the parents there. Okay. So this would become probability of M given all of these other guys. We're going to remove all of them and we're only going to leave the parent. Okay. This is only true if the parent is already here. But let's say if I said something like this, probability of Mary given John, can I say that this is simply equal to probability of Mary given the alarm? No, because this set does not include the parent. Okay. But could I say that the probability of Mary given John and A, is this equal to probability of M given A? Yes. Why? Because the parent A is actually part of the set J comma A. Okay. So I hope this equation 14.3 makes sense. G. Will it give us what answer? Okay, so if you keep the condition, will it give you the same answer? Yes. So these two things are equivalent. Okay, that's a good question. That if you had both of these, actually all we're saying is that one of them is redundant. Okay, this is equal to this because this is actually not having any impact. It's again the conditional probability. You understand? Remember what we're talking about, the conditional probability. We said that given, so going back to conditional probabilities, way back over here. Where were we at the conditional probabilities? We said that the probability of C given B is independent of A. Okay, same thing that we talked about over here. The probability of let's say this event given this is independent of the previous one. However, you could give those, but it doesn't make any difference. Okay. So so basically what we're saying is that we can remove this over here. Okay. So what could we remove over here? Probability of J that John calls, given all these other chaps. Can we simplify this? This is simply the probability that John calls given that A. Okay, why is that? Because A is the parent and we simply want to reduce it to the parents. Okay, so this is another important equation, 14.3, that will come in handy. So this is kind of obvious that probability of J of M given all the other chaps is simply the probability of M given A, which is 0.7 over here, and this is simply 0.9. Okay, the idea was sort of to confuse you with additional variables which are unimportant, but now you know that you can actually remove them. Okay. Now, again, this is the original question that I had posed. Probability that you have a burglary given that John calls. Okay, now this is going 2 levels deep. And this becomes a lot more complex. And I really don't want to get this course to be that complex, so I'm not going to actually solve this. Okay, all I'm going to say is that there are software solutions which can make your life a lot easier. Okay, and you can put all of these values in one of your favorite, and there's no clear-cut solution. I think one of these I've actually used many years ago, it's Genie, but there are probably other solutions today as well for solving Bayesian networks. If you look up tools for solving Bayesian networks, you'll find a whole bunch of tools. Okay, and what they'll allow you to do is to put conditional probability tables. Okay, and you'll have independent probabilities and you'll have conditional probabilities, and then you can ask all kinds of causal relationships and other more complex questions as well. Okay. So this is the extent to which I'm going to cover the previous chapter. And now I would like to go over something because we do have a fair amount to cover in this course. So I'd like to now go over the next stage. And I think this is chapter 14 of the book. And this now says, what happens when you have time involved? Okay, and this is a more realistic scenario where you do have time involved. Okay, in all real world cases, things change over time. Things are not static. Okay, so now we're going to look at what happens when time is involved. All right, and in order to understand this, we're going to start by looking at some concepts which are derived from stochastic processes. And the term stochastic processes, you have whole courses which are very advanced level, but we're going to look at it in a very basic level. Okay, and we're trying to understand what stochastic processes are, and we're also trying to understand what Markov chains are at a very basic level. And we use these basic concepts to be able to solve something like Markov decision processes. Okay. So let's try to understand what is a stochastic process. So whenever you talk about a process, and it doesn't have to be using the word stochastic, it could simply be called a random process. Okay, it's simpler to understand because we've already understand random variables. All we're saying is that when you have a random variable and you have a bunch of random variables over time, then we can call it a process. Okay, so think about a simple coin tossing example, right? Suppose you do two coin tosses. So in the first case, you could have head or tail. And in the second case, you could also have heads and tail, right? So this was at time t is equal to, let's say, 1. And this event was at time t is equal to 2. Okay, so now you're doing experiments in time. Okay, so these are random variables x, but now x, this is at time 1, and this is at time 2. Okay, so now the experiment is continuously being done over different times. Okay, and time is progressing either continuously or discretely. Okay, so let's try to look at some real world examples, try to understand stochastic processes. So basically all we're saying is that it comprises of X, and X depends on T. Okay, so X could be, for example, the output of your coin tossing or your your dice roll, and T could be different experiments that are conducted over time. Okay, now both of these variables could either be continuous or they could be discrete. Okay, so there you can see that you could possibly have 4 possible combinations, and I've written this down as 1, 2, 3, and 4. So think about the first case. The first case is where both T and X are continuous. Okay, then you can have the other combination where they're both discrete. Okay, both X and T are discrete, and then you can have 2 other combinations where X and T can be discrete or continuous. So let's take a look at all 4 possible combinations, and let's try to relate it to some real world cases. Okay, so now you need to tell me real world cases where X is continuous and time is continuous. Okay, anything that changes over time, where time is continuously changing and the value of that variable is also continuously changing. G. Okay, so chess game. So in chess game is when you take steps in chess. Okay, so good example. Let's look at it. In chess game, is time continuous? Or actually, are we only looking at those events where you've actually taken steps? Time is continuous, but we've actually discretized time. So for example, when we did the chess problem and looked at what are the different branches, we don't look at all the times when you were actually thinking, right? We only said, okay, here is one possibility, and then in the next probability, this is the next event. So we've actually discretized time, and we're saying that we're only looking at those times when you've actually taken an event. So essentially, we've discretized time in the chess case as well. Okay, so we're going to, so in chess, for example, we could say at time 0, actually it'll be this case. So I'll give you a hint. It'll be where both are discrete and the values are discrete as well. So let's look at this. At times t is equal to 0, you started your chess game. Okay, at some time later, at let's say time t is equal to 1, you made your first move. Okay, in that first move, could you have any possible values, or are the possible values discrete in chess? They're discrete, right? Because obviously you can't have the pawn in between two places, right? They're only it's extremely large values. It's probably 10 to the power 40 or 10 to the power, I don't know, 100 maybe, the possible values of the discrete possible values that you could have in the chess game, but they're all discrete. Okay, the pawn can either be in the first square or it could be in the second square. The queen can only be in one of those squares, right? But it can't be in any square in the middle. So in the case of chess, it is actually both time is considered to be discrete and the values that your state can have are also discrete. Okay, so I hope you're convinced of that. Let's look at more examples so that you understand what we're talking about. Think of other examples. जी आप बताइए. Radioactive decay. Okay, so what you're saying is that let's say that the amount of decay is alpha. Okay, and it is slowly decaying over time. Now, do you think time is discrete or continuous? It has to be continuous, right? Because the amount of decay could be, it could start off with a value, let's say the amount of uranium is 1 milligram, right? In the next microsecond, it's going to be slightly less. So which of the 4 cases do you think it's going to be? Sorry? Case 1, right? Because not only is time continuous, but the value of the uranium is also continuously changing. So you can say that decay is actually a continuous process. It will probably start off over here and it will slowly decay over time. Okay, it's not actually very stochastic, to be honest. It can actually be predicted by by an equation. But it is but in terms of the process, the time versus in one of these quadrants, yes, it would fall in the first quadrant. Other examples. G. Sorry? Aging. Very good. So where would aging be? So let's say our age, right? So is our age discrete or continuous? Well, so if you look at it as number of years, and when you celebrate your birthday, yes, it's discrete. But a millisecond from now, are you actually going to be aged? Have you actually aged? Yes. You may not realize it, but every microsecond, your hair, one of your hairs will probably become maybe a little grayer. All right, until you get to my stage when you lose all your hair, then it doesn't matter whether it's white or not, okay, or black. But for every millisecond or every microsecond or every femtosecond, you are aging. So which case is it? Case one again, because time is continuous and your aging is continuous as well. But you could convert it into another one of those problems. So suppose, can we convert it into this problem? How would we convert the aging problem into a discrete and discrete problem? G. Yes, so exactly. So what we could say, let's only look at your birthdays, right? So we could say that time 0 when you were born, right? And you were, let's say, 0 aged. And then at 1 year later, your age was 1. And 2 years later, your age was 2. And 3 years later, your age was 3. It goes straight. It's a very simple linear equation, but it is discrete both in time as well as the x values. Okay, so you can actually take any real world problem and try to fit it into any, it depends on how you're looking at those t values and x values. Okay, think of other values, other examples. G. Somebody else, you talked about the traveling salesman problem. So how would you frame that problem? Okay, so remember in the traveling salesman problem, what we're trying to do is, let's say we are using a technique where we're using, let's say, a genetic algorithm. We start off with a random solution, okay, and then we try to come up with better and better solutions. So that initial random solution, is that one of, could you have infinite possible values, or are those discrete? It's discrete, right? So the traveling salesman problem has x being discrete, okay? So it's going to be over here, it's going to be either 2 or 4. Now what about time? As you're solving that problem, are you looking at continuous time or are you looking at discrete time? Discrete time, right? So you're taking steps. You're trying to solve it, what happens when you do, in a genetic algorithm, what happens if you do, a mutation or what have you, okay? So time over there, we've converted that into a discrete and discrete problem, okay? Now think of more stochastic problems, things which are not as, predictable, but less predictable. Where aging is predictable, your decay problem was predictable, the other problem maybe is not as predictable. That's probably a good one. But think of more real life problems where it's less predictable. G. I want to pick other people as well. Did you raise your hand? Or who else raised their hand? Somebody who hasn't answered yet? Okay, go on. Amount of rain, yeah, so that's a good stochastic problem, right? Stochastic means that the variables as you're going forward are somewhat unknown, they're random. So if you look at, if you think about the amount of rain, let's say in Karachi, in which category would that be? Could you consider that as a discrete, or discrete? Could you convert it into any one of those 4 cases? Originally, is it continuous? Is it, if you think about the original thing, so if you look at a very small time interval, right? So if you look at the time interval between now and 1 second later, okay, you could say that time could be continuous, but an easier way to think about it is to make time discrete, okay? You could say how much rain falls in Karachi on a single day, okay? So that's converting the time into discrete, okay? Now, what about the amount of rain? Is the amount of rain continuous or discrete? So the amount of rain is continuous. So this is a good example of which case. So here time is discrete and x value is continuous. So it's case 3. Okay. So case 3 is basically saying that we look at, let's say, day 0 or day 1, right? And we say, what is the amount of rain that fell? And the amount of rain that fell could be, maybe it's extremely small. It could be 0, for example, over here. But let's say tomorrow on day 2, the amount of rain that fell was, I don't know what the units are. It could be 0.01. Okay, 0.01 liters in that entire day. Okay, on another day, on the third day, the amount of rain that fell was maybe 0.3 on that third day. So basically, what we're saying is that the amount of rain is continuous, but we've discretized time. Okay, so this is an example of case 3. G. So say that again. So you could take time as intervals of days, or you could say the year. So you could say that this is the first year, and this is the amount of rain that fell in that year, and this is the amount of rain that fell in year 2, and so on. So you could take any particular value. Okay. Think of, okay, so we're going to stop over here, but we'll come back to this and think of more examples, because so far we haven't looked at this case, and we haven't perhaps looked at other cases. So think of other examples, and we'll talk about these in the next lecture. Moving what? Moving train. So the speed of the train, let's say, and so time is continuous. So yes, so absolutely. So that would be which case? This is continuous as well as time is continuous, right? So in other words, the speed of a train over time is absolutely in this case, right? It could actually go like this. Okay. Hopefully it doesn't go like that, otherwise you have problems. Okay. But maybe if it goes slowly, it will go up and then get to a certain special value, and then it'll come down, right? So before it stops, it slowly stops, and initially it accelerates. Okay. So you might have come across this when you studied physics. Okay. So that was continuous time and continuous speed.